Hello, students. Hope you are doing good. Today, I am going to do a recording on Riemann sums. Riemann sums is an important concept in Calculus 1, and they are used to approximate area under the curve, right? So, last time in the last recording we saw area under the curve is represented by the definite integral, or the net area between the curve and x-axis is represented by this definite integral a to b f of dx. This is actually the net area between f and x-axis, right? So it's the net area between f and x-axis. Now, if a function is known, you can actually use fundamental theorem of calculus to find its antiderivative and then apply the limits, upper limit minus the lower limit. Now, if the function is not known or certain data is known, then you need to approximate. You cannot actually find the antiderivative since the function is not known, but you can actually use, or you can actually approximate the area under the curve using that function, so using that data given. So let me take an example here. If you have a curve, let's say that's the curve. Basically, I'm taking y equals x squared, but what I'm doing is I'm taking 4 points on it. So the first point, the second point, the third point, and the fourth point. The first point here is at 1, the second is at 2, the third is at 3, and the fourth is at 4. And since it's y equals x squared, right, I'm just taking this example so that I can tell you what the approximation is and how this approximation is different from the actual value. But suppose the only things you know are the points, which is 1, 1 here, 2, 4 here, then you have 3, 9 here, right? Y3 and x3 and y9, and then you have 4, 16 here. And what you want to do is you're looking at my graph is a little bit off, so let's see this. This is my point 4. So suppose you're looking at this area right here, right? So how would you approximate this area? If a function is known, you can find the antiderivative and then use the two limits, and that is your fundamental theorem of calculus. Now, if a function is not known, you can approximate area under the curve, but that approximation is done using Riemann sums. Okay, so what I'm going to do is I'm going to draw another neat graph of this function and show you what kind of Riemann sums can we use here. So this is my graph, and let me take these 4 points first. So the first point here is 1, then 2, then 3, 3 right here. Oops. So 3 and then the fourth one. Okay, so let's say this is my 0 to 4, and the point here is this is 1, this is 2, this is 3, and that's 4. Okay, so one second, so let me erase this part, I don't need it. Okay, so what I can do is this is a curve right here, right? The function, it's not a line. It's not a triangle that I can use a formula, or it's not a rectangle, or no specific geometric figure so that I can use a certain formula to find the area under this curve. This is right. So what I can do is, I don't know the area of this curve, but I can approximate using areas of the geometrical figures that I already know. For example, if I start to draw rectangles here, let me choose a different color here. So suppose I'm looking at drawing rectangles here, something like this. One rectangle, this is my second rectangle, and that's my third rectangle, and the last one is my fourth rectangle, right? I can still approximate. This will give me an approximation of area under the curve. Not a very good approximation, but still it will give me an approximation of area under the curve. For example, for the first rectangle, this width for all the rectangles is 1, right? 1, 1, 1, 1. That's the width. Now, what's the length of this first rectangle? The length of the first rectangle is actually the y value at 1, which is 1 because that point is 1, comma 1. So it's 1. So 1 times 1 plus length times width. For the second one, the y value is 4 right here, right? So 2 comma 4. So for the second one, it's 4, length comma width, still 1. For the third one, the y value at 3, the height over here, the height or the length is actually the y value. So it's 9 comma 1 and plus the next one is 16 comma 1, right? So these are the 4 rectangles, which gives me an approximation of area under the curve F, right? So which is 1 plus 4, 13 plus 9, 22 plus 16, right? So 1 plus 4, 5 plus 9, 14. So it's 30 actually, right? So the area under this curve, basically I'm approximating this, x squared dx from 0 to 4, right? I'm approximating this. The actual value of this is, if I use my antiderivative, it's x cube over 3, which is nothing but 4 cube over 3, which is 64 over 3, and that's 21.33, right? Oops. 21.3. So it's off. It's an overestimate. This one is an overestimate. Since you can see, this is the area. This is the more area that we have taken into account using these rectangles. So this is giving us an overestimate in this case. We are taking into account this area also, the shaded one, the blue shaded one, right? But still, finding something is actually better than finding nothing. It's again, as I said, it's nothing but an approximation of area under the curve F, right? Now note here, I have divided 0 to 4 into 4 intervals of equal length, right? I have divided 0 to 4 into 4 intervals of equal length, each length as 1. So first interval is 0 to 1, then 1 to 2, then 2 to 3, and then 3 to 4, right? And I have used the length corresponding to the right hand one. So for example, the four intervals are, the first is 0 to 1, then I have used 1 to 2, then I have used 2 to 3, and then I have used 3 to 4, right? And I have used the lengths corresponding to the right end points. So first I have used, in the first rectangle, I have used the length corresponding to 1. In the second interval, I have used the length corresponding to 2, right? That's the one I have used for the second rectangle. For the first, I had used 1. For the third, I had used 9. And for the fourth, I had used 16, right? So I'm using the right-hand endpoints to determine the rectangles. Can we use left-hand endpoints also? That would also give me an approximation. So let's change the color here and let's use, I have taken blue, so let's use green. So let's use the left-hand endpoints. Between 0 and 1, the left-hand endpoint is 0, right? And the length at 0 is 0. So basically, I'm not taking anything for the first one. For the second one, between 1 and 2, I'm going to use this length here and draw a rectangle, right? Between 2 and 3, I'm going to use this length right here, this one, and draw a rectangle, right? This one. Between 3 and 4, I'm going to use 9, not 16, and I'm going to draw this rectangle. So again, you have 4 rectangles. The lengths are a little bit different. In this case, I'm leaving out some area, right? I'm actually underestimating the area. So for the first one, in this case, I'm doing it with green. It will be 0 times 1, which is 0. Second one will be 1 times 1, which is 1. Third one will be 4 times 1. And fourth one will be 9 times 1. So in this case, I actually have my answer as 14, right? So this, by taking the left hand endpoints, I'm getting 14. By taking the right hand endpoints, I'm getting 30, which are my blue ones, which was my overestimate. And 14 one is my underestimate. more closer or little less error in the left hand endpoints, because that's 7 off from the actual value, which is 21.3, and the right hand endpoints are actually more off, so more error in the case of right hand endpoints, right? So there are ways to reduce this error. Some of them, so if you add the number of rectangles, you can actually see the error is reduced. That's one of the ways. Or you can average these out. If I average these out, I get 44 divided by 2. You add these two and divide by 2 and you get 22. You are getting closer to the actual value. And the other way is by using midpoints instead of using the left or the right points. That's actually one of the best ways of using Riemann sums for calculating area under the curve. So let me show you let me draw the rectangles here, and maybe I'll do the calculations on the next slide. If I'm looking at the left hand endpoint, if I'm looking at the midpoints, instead of using 0 or 1, I'm going to pick a value in the middle, which is 0.5, take the height corresponding to that value and draw a rectangle. So something like this in the first one. Okay. Pick a value between 1 and 2 in the middle, which is 3/2, right? 3/2. The y value at 3/2 is 9/4 because it's y equals x squared. So go on both the sides and fill up the rectangle. So that's my second rectangle. Similarly, over here, it will be 5/2 corresponding to 5/2. My point is right here. Go both sides and fill up the rectangle. So that's my third rectangle. And the fourth one comes here, which will be 7/2. My y value will be 49/4, and fill up the rectangle. So you can see in the purple ones, I'm losing something, but I'm gaining something also, right? I'm losing this part right here, but then I'm gaining this part right here. So that kind of balances out. And that is why the midpoint approximation or the midpoint Riemann sums are the best way to approximate area under the curve. May require more steps. The calculations are a little tedious, but who does calculation by hands these days, right? So Microsoft Excel and computers programs are more than efficient in using midpoints as compared to the left or the right Riemann sums. We don't do 4 intervals, we don't do 5 intervals, we actually do hundreds and thousands of intervals, as long as the computer can take that number, right? So let me show you the midpoint calculation for these 4 intervals. So what happens is your intervals are 0 to 1, right? Then 1 to 2, then 2 to 3, and then 3 to 4. Right? You have chosen the midpoints. The midpoints here are 0.5, which is 1/2. Then you have 1.5, which is 3/2. Then you have 5/2, and then 7/2. Right? The y value for all these midpoints are 1/4 because it's the curve x squared. Then 9/4, then 25/4, and then 49/4. Right? Okay. So these are the lengths you'll be taking. The width in all these cases is still 1. The width of the rectangle, if you go back, the width is still 1 in all these cases. So the width is still 1, 1, 1, 1. So what's the area? Area is just length times width. So 1/4 plus 9/4 for the second rectangle plus 25/4 plus 49/4. And if I add them 10, 25, 35, plus 49, it's 84/4, which is 21, which so far is the closest, even closer than the average that we calculated, right? So far, the best approximation is the midpoint is the first one, right? The second one is the average that we took, right? The third best is the left-hand endpoints. And the fourth in this case are right. The left and right could fluctuate, but the midpoint and average are midpoint is usually the first and the average is the second. Later on in Cal 2, you will learn another approximation which is called the trapezoidal rule, and that's actually pretty good. Has some advantages, some disadvantages, but midpoint so far is the winner for approximating area under the curve. Okay. So if I increase the intervals, probably I don't know if I can handle the calculations here, but if I increase the intervals instead of 0 to 1, I can make them half the length. The second one is half to 1. The third is 1 to 3 halves. The fourth is 3 halves to 2. Then you have 2 to 5 halves. Then you have 5 halves to 3, then you have 3 to 7 halves, then you have 7 halves to 4, right? You should have 8 intervals. I've divided my 0 to 4 into 8 intervals, 1, 2, 3, 4, 5, 6, 7, and 8 intervals. Now using the left hand sum, I'll be picking the left hand endpoints, which is 0, then 1/4, I'll picking this and then calculating the y values, then 1, then 9/4, then 4, then 25/4, then these are all the y values, then 9, and then 49/4. You should have 8 values, 1, 2, 3, 4, 5, 1, 2, 5, and 3, 8, right? And then what is the width of each interval in this case? These are the lengths, these are the y values. The width in each case is 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, and also in this case, all these cases, it's 1/2, right? So for all the intervals, you are actually drawing the rectangles, but smaller rectangles in this case, right? So how would you find the area? Length times width, 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 and go on adding. Now, you may want to just add the lengths first and multiply by 1/2 at the end. You can factor out 1/2. So basically I'm adding 0, 1/4, 1. So basically what I'm doing is I'm adding 0 plus 1/4 plus 1 plus 9/4 plus 4 plus 25/4 plus 9 and plus 49/4, right? So basically you are adding this, and if you add this, if I have it in my notes, I don't know, you probably would have a better approximation. This is, I think 17.5 or something like that, but so this is 145 and 914 if I adjust the whole numbers, and then 1 plus 9 10 plus 25 35 plus 49 is 84/4. So 84/4 is 21, so that's 35, and then divided by 2, it's nothing but 17.5, right? This is my left hand sum using 8 rectangles instead of 4 rectangles, using 8 intervals instead of 4 intervals, right? So so earlier it was, what was the earlier value for the left hand endpoints? It was 14, right? And now it has gone up to 17.5. So using 4 rectangles, it was 14. Using 8 rectangles, it's 17.5, right? 8 number of rectangles, number of rectangles, and that's and this is the midpoint. This is the left hand endpoint, left sum, 17.5, and these are the rectangles, right? 4 and 8, and the actual value is 21.33. See, if I increase the number of rectangles here, the value got closer to the actual value, which is 21.33. And similarly, you can see using the right. Similarly, you can see the difference using the right one, which was 30, and I don't remember. It should go up to, I don't remember, but it should go down, actually, not up. It should go down to in 20s for this case. Okay, if you want, I can calculate. So you'll be having these, but for right hand you'll be using 1/2. So you'll be starting from this particular value, and then you'll be adding a 16 at the end, which is 4 square. So that would give you 14 plus 16 plus 21. So it's 30. So it's 51. It's 51 over 2. So that would be 51 over 2. So that's approximately 21.5, right? So sorry, 25.5. So that's coming out to be 51. So see, it has gone down. The right one has gone down, the left one has gone up, and by increasing the number of rectangles. So that's one way of making your approximation better. Another way is to use midpoints. 8 rectangles, midpoints, you will be at a very good number, okay, for this particular curve. So lot of advantages. If the data is given and the equation of the curve is not given, you can certainly use this for approximations. Usually we use Excel or other programs to find area under the curve, but the formulas should be correct. The concept should be correct in order to use Excel and other mathematical softwares, right? So that's about Riemann sums, and the next recording I'm gonna send you is about U substitution. And so stay tuned and hope you're doing good. This is the end last week, so keep working hard and shoot me a question if you have any. Okay, take care. Bye bye.